Owned objects live in wallets, immutable objects preserve history, but real-world dApps often need a single focal point that everyone touches. An order book, a vote tally, a game lobby. On other chains, that role falls to a privileged address that alone can mutate state. SUI's answer is the shared object, one resource published to a well-known address that any transaction may reference. Parallelism survives because the scheduler grants a short-lived write lock to exactly one transaction, while non-conflicting operations on other objects keep flowing. The price of open access is coordination. To prevent double writes, a shared object embeds a monotonically increasing version. Your payload says, I plan to update Marketplace v17. Validators grant a write lock, execute, bump the version to 18, and commit. If in the meantime someone else already sealed v18, your transaction arrives stale and reverts. Wallets simply fetch the new version and retry. Crucially, read-only calls still succeed on the last stable version, so analytics dashboards never stall. Publishing a shared object is a one-way door. You mint it exactly like any key resource, then shift it into the global bulletin board namespace with transfer::share object. From that moment, no wallet owns it. Its address, often at 0x0 for singletons, is the rendezvous point hard-coded in all future transactions. That address now unlocks lightning-fast parallel reads because validators can hash partition storage by object ID. Openness doesn't mean chaos. In our marketplace, everyone may read listings, but only trusted curators should create a collection. Instead of embedding admin addresses, we mint a capability, a resource token that confers exactly one power. Because the cap itself obeys key plus store, it can travel wallets, be escrowed, or even sold, yet it cannot be duplicated or silently lost. The entry function simply takes enlisting cap. If the caller lacks it, the compiler won't satisfy the borrow and the VM aborts. You get least privileged security enforced by the type system. SUI's scheduler evaluates every payload's object set. Suppose two sellers list NFTs in the same marketplace block. Only one listing actually mutates the marketplace table, so it wins the lock. The other aborts instantly. No partial writes, no poisoning. Read-only queries keep flowing because they borrow a historical snapshot. Meanwhile, hundreds of other shared pools continue unaffected. This deterministic contention model is miles easier to reason about than gas auction optimistic concurrency on some chains. Voiceover. Init creates two resources, the singleton marketplace and a listing cap. We immediately call transfer.share.object.imp, locking its address forever at 0x0. Listing cap is transferred to the deployer. Their wallet is now the curator. The shared object contains a table mapping a collection address to a vector of token IDs. Anyone may call get listings. Only a transaction that carries an immutable reference to the cap may enter list. We don't even check sender. Possession is the proof. Inside, we mutate the vector and emit an event so off-chain indexers update instantly. The compiler enforces that the write lock covers only marketplace. Token ownership remains untouched. This scenario spins a local ledger, deploys the marketplace, then proves capability enforcement. We first call list with a valid cap, vector length increments. Next, we intentionally omit the cap reference. The test harness expects abort code 0 and flags success when the VM indeed bails. This pattern gives airtight evidence that no silent path exists around your access control rule.